So there is homework due tomorrow. I hope you've had a chance to check it out. See what you think. Um, okay, sorry for the delays. I want to talk about something a little bit new. You know, we're still talking about Turing machines, but we did many examples about make me a Turing machine that accepts this or that language, and we're sort of done with that for now. Um, Another topic about Turing machines is called. Hopefully you'll be able to read this. No. Can anybody see that? It's like I need a fatter pen. Let me try. That's no better. This pen is dead anyway. Can you see the first Turing that I wrote there? I'm going to try hard to say everything out loud. What I want to talk about today is Turing computable functions. The idea behind this topic is thinking of the Turing machine not as a thing which either accepts or rejects a string, which it is, and you can think of it that way. But you can also think of the Turing machine as a general purpose computing machine. So I'm going to say the Turing machine is a computing machine. You could say computer if you want, although that's a little suggestive given our modern usage of the term computer. The Turing machine is a computing machine which takes some kind of input on the tape, and after doing its thing, whatever it does, it ends up with something also on the tape. Now, usually we think of, so far we have thought of just what's on the tape at the end doesn't really matter. It's just, is it accepted or not? But what I want to talk about for a little while is thinking of the machine as something which begins with something on the tape and then ends with something on the tape. So the machine takes input on the tape and ends with some output on the tape. Right? Now, the machines that we've been doing lately, the output is usually like x or something, because the procedures that we've been using have to do with, you know, turn this into an x, and then turn this into an x. And if you keep doing that, the output is not very interesting. By the time you get to the end, it's just a bunch of x's or something like that. But I'm going to talk about machines which are specifically designed to have some kind of interesting result on the tape at the end. All right, this is the same. The machine, the way it works is the same. It's just a very different way of looking at it and what it is used for. So here is a very simple example of what I mean. Move. Simple example. Here's the machine, and I would like us to try to think about what does this machine do to the tape. So it has a starting state from which it has this arrow AAL and also BBL. And then another state from which there's an arrow blank AR, let's say, and then another state. All right. So this machine and all the machines that we draw, you know, today when we're talking about this topic, does not have an accepting state, because I don't care about accepting, rejecting. All I care about is what does the tape say when it stops. So it doesn't have an accepting state, but it will eventually stop. Like it will just get stuck at some point. And I want to know, what does the tape say when it gets stuck? So can we, I mean, look at the machine here and see if we can think about. You got an idea?
Does it end with an
I think it does end with a A, but not just a A, I would say. Let's imagine we start with, let's say we start, I'm trying to scroll just a little bit. Let's say we start with, you know, some string X on the tape. So the way I would indicate that would be, you know, I don't usually draw the tape, but it'd be something like this. And let's say this is the starting position on the tape. And when I say the tape has X on it, what I mean, X of course takes up more than one letter, but X is written, you know, here, 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 whatever, however long X is. That's where you'll see it on the tape. And then what does our machine do? Well, see all at once. My alphabet, by the way, in this example is A and B, right? Little a and little b are the letters. So what the machine does is, from the starting state, it immediately moves one position to the left, right? And it keeps the same whatever it was pointed at. If it's at A, it stays at A and then moves to the left. B stays at B, moves to the left. Then what? Then the second state there, this arrow says blank A right. And so what's going to happen is this turns into, and then it stops, right? So really this is just, it only does one thing. It moves to the left once, and then it does this. So it turns into, same picture, same stuff over here, whatever this is X. But then right here, used to be blank, now it's going to be A, right? And then I guess the head moves, it says moves to the right again, although that doesn't really matter, but the head ends up pointing at this location again. All right?
We can't see the...
Oh, so what happened? I think you're stuck.
Yeah, I think you're just putting it sort of on the camera.
No, because I can see it fine on my screen. I'm moving it and nothing's happening up there. Oh, it's cropped in a weird way.
Yeah, I think the TV crops your screen.
Okay.
It gives you
Okay, so I gotta look up there and not. Oh yeah, I see that now. I don't know if that's my. Are you cropping it? I don't know. You can't crop it, right? Yeah. All right. Sorry about that. Thank you for. See it now? Yeah. There's like a very small area of my paper I need to confine myself to. Okay. So I hope that you could follow what I was just saying. If you begin with X on the tape, right? What the machine does is it starts here, it moves to the left, puts an A there, and then moves back to the right again. And what remains, what you end up with is like this. All right, so can I say in the summary, we start with X on the tape. See that? Yes. We start with X on the tape, and the Turing machine, this is the language that we use for this. The Turing machine halts, that is, it does whatever it does until it stops, right? The Turing machine halts with, what's going to be on the tape when it halts? What's the string that you see on the tape? AX, right? This tape now says AX. The Turing machine halts with AX on the tape. So we can think of this as a machine that starts with X and turns it into AX, right? That's what the Turing machine does in this sense of as a sort of a machine that does something, right? So in this little section, we are thinking the Turing machine not as a thing which either accepts or rejects a string, but a thing which takes a string as input and does something to it and gives you some kind of answer. All right. So in this way, the Turing machine is acting like a function, right? It has some input and it gives you some answer as the output. And in this example, you can easily say it is this function, f of x equals ax, all right? Whatever the input string is, you just put a on the left side. And we can actually say, what's the domain and the codomain of this function? It would look like f, you put the colon. So what is f in this case? You can plug any string you like on a's and b's. So the set would look like this. AB star, that is the domain, is all strings which are made up of a's and b's. And what does the answer look like? It also looks like a string which is made up of a's and b's. So I will say this is a function like that, right? These are stars. Hope that doesn't look like a K or something. Its domain is all strings on a's and b's, and the answer is another string with A's and B's. All right? Could we do other sort of variations like this? This is what we're going to try and make Turing machines. The basic setup is I tell you a function, you make me a Turing machine that does that function, right? And then eventually we'll talk about like what kinds of functions could you possibly do on a Turing machine? Or are there certain functions which you can't do on a Turing machine? That kind of thing. But anyway, we'll get to that in a moment. How about, let's try f of x equals xb. So you have to think sort of mechanically about the Turing machine. What is your strategy to put a b on the end? To put something on the beginning, all you got to do is step once to the left and stick the a on the beginning, right? How do you want to put something at the end? Anyone want to suggest a general strategy? Put something at the end? Yeah. Yeah, move all the way to the right with like a looped edge or something until you see a blank, in which case you change it to a B and then stop, right? I think you can do that really maybe just in one state. I mean, you begin and you immediately start moving over and over to the right. And if you see A's and B's, you just leave them like they are. So I'm going to say AAR here and BBR, right? Moving to the right through A's and B's. When do you stop moving to the right? When you see a blank, right? So I'm going to have an arrow going somewhere else with the blank. And I think we should change the blank to a B, right? Because that's our goal, is to stick a B on the end. So I'm going to say B blank, B R, I guess, although that doesn't matter. And I think that's it. Then the machine should stop. So this is what it takes to put a B on the end. All right? Great. You want to try some? I got some for you to try. You try. Is it too soon? No. How about this one? F of x equals AXB. See if you can put it together. This machine needs to put an A on the beginning and then a B on the end. And then I got another one. This is two separate ones for you to try. AXB and also F of x equal epsilon. See what you think about that. I'll give you a few moments. All right, looks like people are doing pretty well. Let's try these. So the first one you can do by kind of putting our two previous examples sort of in series. So to do this AXB thing, I want to do something like first, so this is f of x equal AXB. First I move to the left by one position, and I don't know if my string begins with A or B, so oops. I have to move to the left if it's A or a B. And then I'm going to change a blank to a A. So this creates the A at the beginning. So it's going to say blank A R. And now we have added the A at the beginning, and we're now pointed at the first letter of the original string, the X. Now we need to move to the right over and over again, all the way to the end. So I'm going to say AAR, BBR. When you get to the end, which is a blank, you make it into a B. So blank, B, R, I guess. And that's it. I think that's all it takes. So right here is where the A is added to the beginning, and then right here is where the B is added to the end. All right? And what about f of x equal epsilon? So this machine should just erase everything on the string, right? And I think that once you think this through, it's not so hard to do. You just do one of these sort of loopy things, moving to the right, and every time you turn everything into a blank. So I think all it takes is just one state. A blank R, B blank R. All right? This will just go down the whole string, blank everything. Eventually you'll see a blank, and then the machine stops because there's no outgoing arrow with a blank on it. That's all it takes. Any thoughts on that one? Of course, with all of these, it's possible that you wrote something maybe a little more complicated that does the same thing. That's fine. I'm okay with that. All right. Excellent. This is the kind of thing that, like, I don't know if you talk to your friends about this class. When your friends ask you, what is that class about? You say, I don't know. You might say something like, it's kind of about sort of the theoretical capabilities of different types of computers. And they'll be like, oh, you mean like a desktop or a laptop? And you say, no, like none of those, not that type of computer, not like a real one. But I think maybe what your friend has in mind is actually a bit more similar to this kind of thing that we're talking about right now, which is, I'm talking about the Turing machine as a machine which does something and gives you an answer. And we're talking about what are the capabilities of that machine. So a little terminology about all of this. Like I said, a big question that we're going to ask is, what types of functions can be done using a Turing machine? What types of functions can be computed on a Turing machine? All right. Now, just because of the way we've made our definitions, Turing machines can only do functions involving strings. But you could think, I mean, what if you want to do like numerical functions? Well, you can write numbers as strings. You could imagine, I mean, you could ask yourself, is it possible to make a Turing machine say where you give it a string where that string is actually a number, and the Turing machine, say, multiplies that number by 2? Is that possible? You should feel like that's going to be very complicated, but maybe it's possible. I mean, who knows, right? These are kind of questions. What types of functions can be computed on a Turing machine? There's a name for such functions. So I'm going to say it this way. So if f is a function which has some domain of strings, and its codomain is some other, set of all strings on some alphabet. So if this is a function for some domain, say S is a subset of sigma star. All I mean by this is it's a function where you can plug some strings into it and you get some strings as the answer, all right? If this is a function, um, we say f is, here's the term for it, Turing computable. Turing computable. If there exists a Turing machine which does what f does. So if there is a Turing machine which, when we start with x on the tape, will halt with f of x on the tape. All right? If that's possible for this function, then your function is called Turing computable. That means it is possible to make a Turing machine which computes your function f. All right? So what we've just demonstrated in these like 4 simple examples that we've done, all these examples, all the f's from above are Turing computable. All right, all the functions that we've talked about the past, 20 minutes, those were all examples of Turing computable functions. I want to do another example. This one's a little more complicated. This one is, let me just say, I don't know if it seemed weird to you that I wrote this. F goes S into sigma star. The domain of the function f does not have to be all strings. It can be a function which is defined only for some types of strings. I just want to do an example like that. Here's an example where f of b to the n a b to the n equals b to the n a b to the n. All right? So this is a function where the things you plug into it, you're not allowed to just plug whatever you want into it. What you plug into it, it has to look like b to the n, a, b to the n. So in this case, the domain set is the set of all strings that look like b to the n, a, b to the n, where n is a natural number. All right? Rather than just an x here, I am requiring that the input have a specific format. Things you plug into f, they must look like b to the n, a, b to the n. All right? And what f does is it just inserts another a in the middle. All right? You will see, and if you think for more than just a moment about this, you will immediately agree, I think, it is a real pain for the Turing machine to insert something in the middle. All right? To put something on the end is pretty easy. On the left end, all you got to do is move to the left one spot and put it. On the right end, you go all the way to the right end and stick it. Putting something in the middle, though, would anyone like to suggest a strategy for that? How could you begin with something, what I'm starting with, will look something like this, and I need to turn this into this. Yeah. Okay. Yeah, so, starting here, move to the right through all these B's, encounter the first A, all right? And then what? Yes, you want to add another A, although it's maybe not so simple, because you can't squeeze an extra spot in there, but you want to elaborate on your suggestion? Yeah.
Maybe change one of the B's to an A and then go to the end and add another B.
Yeah, right. So change this B to an A. I tried to kind of line these guys up, right? This B becomes an A, and then this, which used to be nothing, becomes an extra B on the end. All right, so this is our strategy. There's kind of 2 stages to it. First, we move all the way through all the B's. You see an A, you leave the first A alone, move to the right again, change that B to an A, then go all the way to the end and add an extra B. Can we do that? I think so. How about, so I begin by running to the right through a bunch of little B's, right? This is kind of like programming a computer, like the stupidest computer ever. Like all it can do is like one little thing at a time, right? Actually, DFAs are kind of stupider than this, but I don't know. Okay, so I move to the right through a bunch of B's. When I encounter an A, I should keep it the same and move to the right again. That's because the first A you see, you want to leave it as an A. Okay? Anyone say from this state, what do I want? Another loopy edge or an edge that goes to yet another state? B to A? Yeah, so right now we should be pointing at a B, and you want to change it to A, right? Should I make it as a loop back to this state again, or going out to a new state? I think a new state, because a loop is what you do when you want to do the same thing over and over again. This, what I'm describing, is something that should only happen once, right? So I'm going to go like this. I think he said B becomes A, right? Okay? Somebody else, what should I do with that from that state? Uh-huh. BB, is that what you said? Yeah. BBR. Okay? Right now I am moving through all the other B's. Then what? Yeah. Yeah, when you see a blank, you make it a B. I guess R again, that last direction doesn't matter because that's the end, right? Excellent. So that's not so hard, right? The moral of the story, though, is the Turing machine cannot just insert something in the middle, not so easily. You have to actually work it out in a more complicated way. All right? Okay, I got one more. Well, I got plenty more. I got one more. I think this'll probably do us for time because this is quite a bit more complicated. But how about this? F of XCX. XCX. Charlie, is that somebody? Is there a, yeah, pop star something? I don't know. This is what I want. F of XCX equals XX, where X is in A's and B's. So the idea here is you begin with a string which has a bunch of A's and B's, then one C, and then the same stuff again from the beginning, all right? And actually I'm going to change my mind on this. The fact that it's the same X at the end really is totally irrelevant for the example I want to do. I can't erase here, but really I mean this. It doesn't matter that it's, all I want to do is, it takes a string which has a C in the middle, just one C. Everything else is A's and B's. And it just erases the C from the middle. That's all. So I'll say where X and Y are A's and B's. All right? A string which has a single C in the middle. So maybe it's like A, B, A, C, B, B, right? Doesn't have to be the perfect middle, right? It's just there's a first part and then the C and then a second part. And the result, maybe I could just to get us thinking about how we could do this. The result is these guys stay where they are, right? But then the C has to disappear and these guys have to line up this way. So the stuff before the C can just stay exactly where it is. The stuff after the C, everything needs to shift over by one position. That's what we got to do. All right, I think, so there's an initial, the start of this computation is simple. You just move to the right until you see the C, right? You don't have to do anything at the beginning there. So I'm just going to say, let's start by moving to the right until we get to C, all right? And then what? Anyone want to suggest a strategy for continuing here? Yeah.
Are we going to want to make two separate tracks for see if like the first letter of Y is an A or B?
I think so. Yeah, so from here, you want to, I mean, you got to move to the right to see what that letter is, and then copy it back one position. So and how exactly do you copy it back one position? Like he said, you need sort of two separate tracks. If it was an A, back up once and write an A. If it was a B, you back up once and write a B. Okay, so I'm going to try and write sort of in a little words what to do here. You move to the right until you get to C. Okay, then you move to the right once, because you have to point to the next letter, first of all. So you move to the right once, no matter what you were looking at already. And then you sort of, you read that, move back to the left, because then I have to write it as I go to the left. So I'm going to say move to the right by once, and then I'm going to say, remember this letter? Whatever you're pointing at, be it a or B in this position. By remember, I mean you should fork into two separate tracks, because this is the only way that the Turing machine has of remembering anything. Fork into two tracks. And then move to the left, right? You got to go back to the left. And then after you move to the left, you write that letter, whatever the one that you just read was. So I'll say write this letter. The same this letter that you just did before. And then move to the right one position, because you've dealt with that specific spot. And then you just repeat that over and over again. It's going to go back and forth for each little one, copying each letter to the previous location. All right, a lot of back and forths for this machine. That's how it has to be. Let's see if we can make this machine then. So I'm going to start with, my starting state begins by moving to the right past all A's and B's. You don't have to do anything fancy until you get to the C, right? And when you get to the C, I'll begin by just keeping the C like it is. So I'll say CCR. That C eventually is going to get erased somehow, or like replaced by other stuff. But you might as well just leave it like it is for now. All right, now what? I said before, move to the right. Okay, so what I said on my other page was move to the right until we get to C, and then move to the right by once. So that's what I've done that already, all right? Then you should fork into two paths and move back to the left. So I'm going to make two paths here. I'm going to label them AAL and BBL, right? From the C, you go to the right once. And then if it's an A, you want to keep it as an A, I guess, and then move back to the left. And I'm going to change whatever was there to an A. So this is going to say AAR, BAR, CAR, right? So I moved over to the next spot. I see that it's an A, move back, and then whatever is in that position I replace with an A. Similarly down here. Whatever, if on this track, whatever's in that position, I replace with a B. So this will say ABR, BBR, and CBR. Really, it's only going to be a C the first time through, because there's not ever going to be another C that appears while you're doing this. Okay, so after you've done that, let me see if I can try and write a little example of how this would work. So maybe I have ABA, CAB, something like this. And we begin by pointing at the, we move all the way over, pointing at the C, then we're in this state. Pointing at the A, we move back to the left, replace the C with the A, and then move back to the right. So once we get to here, the thing looks like ABA, AB, and we're pointed at this A. And now, in order to go the next time through this loop, we need to just move to the right and start this whole process again. So really, it's something like this. From this position, we have to move right once more to get to the next letter in the string. And then we continue to go through that loop there. This is a little tricky in my opinion. This is basically it, although there's one thing that's not, that still needs a little doing in this example. Anybody feel like, you should be wondering about what happens at the end, right? You know, in our other earlier classes, we've made sort of a thought about, okay, when is it actually going to be accepted? Now, that's not the issue here, but what's going to happen when you get to the end? There is one last thing that needs to happen that is not described on this diagram anywhere. Anybody feel like? Yeah. Yeah, the very last letter has to get blanked out. Like in this case here, if you had just proceeded all the way to the end, copying everything to the left, you'll be left with one extra, like little b will still exist on the end. And you need to turn that into a blank. And nothing that I've written so far will do that. Actually, none of these steps ever turn anything into a blank. So the question is, exactly where in this process does that happen? Any thoughts? Maybe you could ask yourself, how will you know that you got to the end, first of all? I think the strategy you should use is keep on doing all of this until you do get to the end, and then maybe just like move back and blank something once you get to the end. What do you think?
When you go to 4,
Yeah, this one?
yeah, you'll see a blank.
Yeah, if you see a blank here, that means that you're at the end. All right, so I'm going to pull that off as a separate thing. From that state, if you see a blank, it means you've made your way through the whole thing. And what do you want to do with that blank? I think it should stay a blank. I mean, the point is you want to add more blanks, right? So this should remain a blank. Which way should I move? Yeah, to the left, because remember the scenario I'm imagining is I've copied all these letters all the way. Every letter has been copied one position to the left. The only issue is I need to blank out the last one. So I'll go BBL, and then whatever I'm pointing at there is the extra letter on the end, and it's got to be blanked. And so here I'm going to say A blank, R or L, it doesn't matter because this is the end. B blank R. And also C, it is possible if the Y string was the empty string, the very last letter might already be the C. So this is technically possible. C blank R. There you go. And that is the whole, oops, off the screen, sorry. I put a C blank R on there. That will only happen in the unlikely event that the original string Y was the empty string. All right? Not simple, but it can be done. We got a few more minutes, but I think I'm going to leave it at that if that's all right with everybody. Sorry for my technical incompetence. I will make sure to bring the iPad or my car, one or the other. All right, see you all tomorrow. Do that homework. Bye to the folks at home. Thanks for coming. See ya.